All right, why is sodium chloride referred to as a neutral salt? Well, halides such as chloride, bromide, fluorides, all of those, and the alkaline metals, lithium, sodium, potassium, those metals, they dissociate, they do not affect the hydrogen ion concentration because the cation does not alter the H+, and the anion does not attract the H+ from water. All right, let's look at some more pH and buffer problems. Which of the following aqueous solutions are good buffer systems? All right, so let's think about what a good buffer is. A good buffer is made up of a weak acid and its conjugate salt, or a weak base and its conjugate salt. So let's look at number one. The first one given, nitric acid. Well, we know that nitric acid is a strong acid. I'm going to pull up our list here from our chapter 16 handout. Our strong acids, we know nitric acid is a strong acid. So, nope, that is not going to be a good buffer. Number two, we have calcium iodide and barium iodide. So, both of those are iodide salts. Neither one of those is a weak acid or a weak base. Both of those are iodides, so they are salts. The next one, ammonia and potassium hydroxide. Well, if I look at my list here, potassium hydroxide is a strong base. Because we have a strong base, no, it's not going to be a good buffer. Yes, ammonia is a weak base, but a weak base plus a strong base is not going to be a good buffer system. What about this one? Sodium hydroxide, sodium bromide. Well, sodium bromide, yes, is a salt, but sodium hydroxide, that's the kicker, and sodium hydroxide is a strong base. If we have a strong base, it's not going to make a good buffer system. And let's look at the last one. Nitrous acid and sodium nitrite. There we go. Nitrous acid is a weak acid. It's not on my strong acid list. And sodium nitrite would be its conjugate salt. Let's look at number 28. So we have a buffer solution. It is 0.437 molar HNO2 and 0.318 molar of sodium nitrite. So we're given our acid and our conjugate salt. And we're given the Ka for HNO2 is 4.5 times 10 to the negative 4. So what is the pH of this buffer solution? Okay, so I wrote down my knowns here. I'm given the concentration or the molarity of HNO2, which we know is our acid. I'm given the concentration of sodium nitrate, which is our salt. We're given Ka, and now we're going to use the Henderson-Hasselbalch equation here, which says that to find the pH, we need to find the pKa and then add the log of the concentration of the salt over the concentration of the acid. Okay, if we're given the Ka, we can find the pKa by taking the negative log of Ka. So the negative log of 4.5 times 10 to the negative 4 is 3.35. Okay, so that's our first piece right here. Then we're going to add the concentration of the salt, which we know, divided by the concentration of the acid, which we know. So I'm just going to plug it in, 3.35 plus the log of 0.318 divided by 0.437. Make sure that this whole thing is in parentheses. And I did this part first to get it was negative 0.138. So 3.35 minus 0.138 should give me 3.24 for pH. So let's look at 29. We have a 1 liter solution. It contains 0.318 molar of hydrofluoric acid, HF, and 0.508 molar of sodium fluoride. The addition of 0.095 moles of calcium hydroxide will do what to the solution? We are given the Ka for HF, and we're going to assume that the volume does not change upon the addition of the calcium hydroxide. So what's it going to do to the pH? All right, let's write down what we know first. We're given the concentration of HF, we're given the concentration of NaF. So we know the weak acid and the conjugate salts concentrations, and we're told the Ka for HF. Again, if we know the Ka, we can find the pKa, the negative log of that. So I now know the pKa of HF, and I know these concentrations. So I can plug it into the Henderson-Hasselbalch, and I can find out what my pH is before I add in that hydroxide. Okay. So I found that my pKa was 3.14. I found the log of 0.508 divided by 0.381, which was 0.125. Add those up. The pH of that solution was 3.265. Now what happens when I add the, what was it? Hydroxide, the calcium hydroxide. So when a base is added, it's going to react with the acid and form salt. It told me that I added 0.095 moles, and it was in a 1 liter solution. So I was able to find that that concentration is 0.095 divided by 1. So I know the concentration of the calcium hydroxide. Now, Ca is a +2, OH is a -1, so calcium hydroxide is CaOH2. We know that in 1 mole of CaOH2 there are 2 hydroxides. So to find the concentration of the OH ions, I need to multiply this times 2. So I know the concentration of the hydroxide ions being added. Now let's look at what's happening here. I have my acid, I have my base, HF. So here's my conjugate base. Here's my conjugate acid, right? Acids are a proton donor, so it's going to, this H is going to go to OH, giving me H2O over here. So let's look at my ice table. Initially, I know HF. If I look up here, I have 0.318. That 318 capital M means molarity. We know that I had 0.318 moles of that in 1 liter. So that's why I have moles. That's my acid. My base, we just found out that I have 0.19 moles of base that I'm adding to that acid. I also know that up here, my conjugate salt, that sodium fluoride, I have 0.508 moles. So what's going to happen over here on the left-hand side? What will get used up first? Which one's the smaller number? The 0.19 is going to be completely used up. All that hydroxide will get used up. So I'm going to lose 0.19, lose 0.19, leaving me 0.381 minus 0.19, leaving me with this much of HF, no hydroxide left. And yes, I will have some F minus left. Now we can plug in our equilibrium concentrations into our Henderson-Hasselbalch. So our pKa, which we know from up above, the pKa of HF is 3.14, plus the log of my salt, which is 0.689, divided by the log concentration of my acid, which is 0.191. I could have also written it like this, taken that concentration of my NaF from above and added the hydroxide, and then taken my acid and subtracted the hydroxide. I did that in the ice table. Okay, so I'm going to put these in parentheses and solve for that first, and I got 0.557. So 3.14 plus 0.557, 3.697. So what was it before? 3.265. When I add in that strong base, it went up to 3.697. So the pH will raise. And if you think about it, 3.265 to 3.697. I don't know where that came from. And if you think about it, a base is going to increase the pH. And finally, let's look at number 30. A buffer solution So we know we're going to use Henderson-Hasselbalch again. Contains 0.391 molar of ammonium chloride and 0.388 molar of ammonia. So we know ammonia is our weak base, so the ammonium chloride is going to be that conjugate salt. Now, we have 0.0493 moles of sodium hydroxide added to 225 milliliters of this buffer. What's the pH of the resulting solution? And again, we're using ammonium chloride. So we are given here, the pKa for ammonium is 9.25. All right, let's look at what we know. Ammonium chloride concentration, so I'm going to find how many moles of ammonium that is. 0.391 molar, and we have 225 milliliters of it, so I made that 0.225 liters. So we know how many moles of ammonium we have. And again, I found that by taking, to find moles, is concentration times volume. The ammonia, concentration times volume, so I know how many moles of ammonia, and I was told how many moles of sodium hydroxide I added after the fact. Okay, I'm going to do a nice table here. Ammonium plus my sodium hydroxide to give me ammonia and water. So I know how much initially I have of my ammonium, my sodium hydroxide, and my ammonia. And now I'm going to subtract. Which one of these is going to get completely used up? 0.08, 0.04. Definitely the 0.04. So we're going to subtract. We lose our reactants, we gain product. So here's how much ammonium I have. Here's how much of my conjugate salt I have, allowing me to put that into my Henderson-Hasselbalch. And 9.25 plus the log of 0.1366 divided by 0.0386, and that should give me a pH of 9.8.